Dijkstra's shortest path algorithm has been around a long time, since the late 1950s. And this is a general method used to solve what's known as single source shortest path problem. Okay, this is an algorithm that is a greedy algorithm, which means that at any one point we will take the move that seems best at that point, and it's an irrevocable move. That means that we can't undo and pick something else. Once you take that move, you're stuck with it. But in this algorithm, that works well. That does not work well in all problems. But Dijkstra is a greedy algorithm, and it proceeds in a number of stages. The process begins at a vertex that is known as the source. It will be the single source. And then at each stage in the algorithm, we're going to select a vertex that has the smallest cost so far. And these are vertices that are known but not yet explored. I will place these in a min priority queue, which I will refer to as the open list. It means that the vertex has been quote unquote seen, but it has not been fully explored. And so once we pull that vertex off, we will then attempt to update costs to lower values, to lower the cost as we move through the graph. This is Dijkstra's algorithm pseudocode. It takes a graph and some edge lengths and a starting vertex, and outputs then for all other vertices that are reachable from the starting vertex. It outputs the distance to or the cost to that vertex. So we begin again by initializing all of the distances to infinity and all of the previous pointers to null. And we set the distance of the starting vertex to 0 because we're already there. And then we create a priority queue, which I call open list. They call it H here in this example. And basically run that loop then, which is while the min priority queue is not empty, delete the minimum value that's in that queue, the minimum vertex, and then for all edges that are connected to that vertex, look to lower the cost to that endpoint. So let's look at an example. What we're saying is we've got some vertex V, and we're looking across maybe to vertex W and vertex U maybe. Okay, to be consistent, I'm going to relabel this as U. And so I've got my vertex that I'm processing, okay, which is what I pulled off. And I'm looking across at a couple of other vertices that are endpoints to edges. And let's say that this one has a cost of infinity. This has some cost X. And the idea is that what I want to ask is whether the cost here, which I will call C1, and I will call this cost C2. What we're asking here is this cost, can it be beat by the cost so far? Because every vertex that gets pulled off has a cost so far. Okay, can this value be beat by the cost so far plus cost 1? So let's say this is 20, my cost so far is 16, and the edge is weight 3. This is a situation where the cost to this node could be lowered to 19. That 19 would be this 16 plus this 3. If on the other hand, this cost was, let's say 15, then 16 plus 3 would be 19, but the cost to this node via some other way is 15. So in this case, we would not update this node. Whenever we see a node on the other end that has infinity as its cost, it really means it hasn't been processed yet. And always in that case, we would take the cost so far plus C2, and the cost here would be 16 plus C2, and that would get rid of the infinity. Okay, so we will do that. That's the update, and we will execute that over and over. But again, putting all of this in the context of an example will hopefully have it make more sense. So this is the algorithm that we will follow in the actual example. It's going to take a set of vertices and an actual source vertex, which we call lowercase v. We set all the values as we saw previously. We insert the first vertex, the starting vertex, into the open list, and the open list is a min priority queue. Okay, min priority queue with respect to cost. And so again, we will remove it. If it's on the open list, it means it's a known vertex, but it hasn't been fully explored. So this, inside this loop, that's where the exploration is done. We will remove it, and then we will look at all of the other endpoints on the other side of U, and we will see whether those costs can be improved by updating the cost and making U the previous vertex for that particular node. Walk through an example of Dijkstra. The way that I address this algorithm is really in a way that is very similar to the A* algorithm. So it does differ a little bit from what you may have seen elsewhere. But I try to put it in that same format as A*, which A* is basically Dijkstra, you could say, is a special case of the A* algorithm. It's one where the heuristic is 0, and in A*, the heuristic can be non-zero. And so this algorithm has been around for a while, and but it's effective. And so let's take a look at it. The function takes two parameters in this case. V is the set of all vertices, and lowercase v is the source, that is the starting vertex. So a key point here is that Dijkstra is a single source shortest path algorithm, which means it gives you the shortest paths from a particular vertex. And if you change that vertex, those paths will change in the graph. Okay, so let's take a look at a graph. We're going to apply Dijkstra to this particular graph. This is an undirected weighted graph. So we'll fill out this table to get the shortest paths information. Okay, so we begin with the initialization, and all of this, as well as this, comes from all of that. Basically is this code here. Okay, that's what we just filled out. Okay, so what do I mean by processing? Processing is the actual vertex that we are processing at this point in time, and that we're trying to use to lower the cost of adjacent vertices. Okay, the vertices will all be shown here with their information, and the open list is a min priority queue, so that it dequeues by the cost, which will be accumulated in this central part of the table. So we will always pick the lowest cost vertex to process next, and if there's a tie, we will take the one that appears earlier alphabetically. Okay, so let's move. So what we've done here is we've set all costs initially to infinity, and we set all previous's, the previous indicator to -1, meaning that this particular node came from nowhere. And we will see that at the end, only the very first node, the node that's passed into this function as lowercase v, that will be the only one that will retain that previous of -1. And we will use that to when we're trying to retrieve the path. Okay, so we have set the cost to, we then set the cost to lowercase v, which is vertex A in this case, to 0. And that is the only vertex to which we have a cost. Obviously, that's our starting point. So we're already at the starting point, and that's why the cost to the starting point is 0. Okay. And so now let's follow the algorithm. So remember, the open list is a min priority queue. And so let's look at that while loop. While the open list is not empty, it's not empty. In fact, there is vertex A in it. Then remove the min cost vertex from the open list. Okay, and when we do that, then A is here, and you see that we have crossed A out from the open list. So at this point, our open list is empty. And now we're going to begin processing the vertices from A. For all the edges that are incident to A, we're going to ask whether the cost at that particular, at that other endpoint from A, whether that cost is greater than the cost to A itself, plus the cost from A to that endpoint. Okay, and if that is true, then we will, if that cost is greater, then we will update the cost and we will make A that particular vertex's previous. So think about it this way. I'm sitting here in A, on vertex A, and I can look across a ravine and I can see B, and it's got a cost of infinity right now, and I can also see C, and it's got a cost of infinity, and I know that the cost to me is 0. Okay, that's this U cost, and I know also that the cost from me to B is 6. Well, B has a cost of infinity right now, and the cost of 0 to me plus the 6 to B makes it better for B, makes this better for B, because B's cost will become 6 at this point. Similarly with C, C right now has a cost of infinity shown right here, but the cost to me is 0, and the cost the cost across this bridge is 3. So if you come through me, you can get to C at a cost of 3. And so these are the updates that are being made in this particular iteration, and there they are. We see that B is now no longer has a cost of infinity, and it no longer has a previous of -1. It has a cost of 6, and its previous is A. Similarly with C, it's got a cost of 3, and its previous is A. And we add B and C to the open list. And so our open list is no longer empty. That's the last line in the pseudocode that you see there that says insert or update in the open list. So at this point, we're done with this iteration of the loop, and we go back to the top, and the open list is not empty. So we're going to remove the minimum cost vertex. Okay, so which one is that? Well, B has a cost of 6 and C has a cost of 3. The remainder are at infinity, and so we will pull off node C, and we'll process that next. And so we remove that from the open list, and now we're at C, and C has a cost of 3. Okay, we can see that in the table up here that C has a cost of 3. And as we look across to B has a cost of 6 now if we go through A, but if we go through C, it's this cost of 3 plus this cost of 2. So B's cost can be improved by C, by going through C, okay? And then D still has a cost of infinity, so D's cost can be the cost of 3 to C plus the additional 3 from C to D, making it a cost of 6. So that can be improved. And E's cost is still infinity, okay? And E's cost can become the 3 here plus the 4 here. So that can become 7, okay? So we make the following updates then to the table. We basically lower the cost to B. It was previously 6, but it is from A, but it is now 5, this 3 and this 2 from C. And we also make a change to D. It was previously infinity here, but it's now this 3 plus this 3, which is 6. And similarly with E, cost here is 3, additional cost is 4, cost is 7. 7 is better than infinity. And so, and we add those particular vertices to the open list. Okay, and so now we look at the open list, and we only look at the things in the open list. That's why we don't consider A anymore. We don't consider C anymore. The only things that are in the open list are B, D, and E. Okay, so we look at those and try to find the minimum value. And the minimum value in this case is vertex B, which has a cost of 5. D has a cost of 6, E has a cost of 7, and F has a cost of infinity. But we haven't obviously even seen F yet. So we're going to pull off B, okay, and we'll remove that from the open list. And now at B I have a cost of 5. How do I know that? I just go to the column B, and I look at the last value. I have a cost of 5 through C. And the question is, can B improve any other vertex that it's incident to? Well, a cost of 5 here plus this 5 would make a cost of 10 to D, but D's already got a cost of 6, so that won't work. C is already out of the game, and because C had a cost of 3, and so we'll never be able to get back to that, right? We already have a cost of 6, and so we can't improve that one. And those and A obviously had a cost of 0, so this particular one gives us no updates. Okay, so processing vertex B gives us no updates, and we're left with the same values that were in the row above. B has been removed, and now only D and E remain in the open list because we did not add anything new to the open list in this iteration. Okay, now out of D and E, so we go back to the top of the loop and we have to remove the min vertex out of D and E. Well, D has a cost of 6 and E has a cost of 7. And so we will take D and we mark it off of the open list, and we begin the process again of exploring. With D at a cost of 6, we look at E, and if we added the cost of 6 at D to the 2 that it takes to go from D to E, that would be 8, and that's not better for E right now because E has a cost of 7 from A to C to E. But F has a cost of infinity right now, and the cost to D is 6. And if I add the 3 between D and F, I get 9. And so F's case is helped. And so we update F, okay, and we show the updates in the brown font, and we add F to the open list where it joins vertex E, which is already there. Okay, and then we go back to the top of the list. We remove the lowest cost vertex out of E and F. Well, E has a cost of 7, F has a cost of 9. So we remove E, okay, and we scratch it off of the open list, and we look, we're at E with a cost of 7, and we ask whether we can improve anything. Well, really, there's only F remaining because the rest have been pulled off. And so E with a cost of 7 plus the 5 to F would be a cost of 12. I can already do a cost of 9 to F, so I will keep that one. So there is no update in this iteration, and only F remains. Basically, when you're down to one node, you pull that off because the open list has to be empty for you to terminate, but you pull that off. But when you're down to 1, none of the updates will be made. Okay, so we pull off F, so we scratch that off the open list, and you notice that the open list is now empty. But F has a cost that's 9, and that's greater than all the other nodes. A is 0, B is 5, C is 3, D is 6, and E is 7. All of those are less than 9, so F can't improve any of these other vertices. And so at that point, we terminate and we exit the while loop. Okay, and those are our final values. So, and the open list is empty, obviously allowing us to exit the loop. So the last entry, really the last changed entry for each vertex. So if you look at each column, the last entry that changed, it indicates the accumulated cost. It is an accumulated cost from vertex A to that particular vertex. Okay, and so let's verify that. A has a cost of 0 to itself. Yes. Okay, because A is a starting point. A is showing B is showing a cost of 5, and that's done through here. And C is showing a cost of 3, and that's here. And I'll explain that in a second. D has a cost of 6, which is done through here. And E has a cost of 7, which is done through C and then E. And then finally, F has a cost of 9, which is done from A to C to D and then to F. Okay, so to get the shortest path then, so the idea, this is called the shortest path algorithm. So we need to get both a shortest path and a cost of that path. So to do that, we're going to start at the destination vertex. That's the vertex we're going to. So if you wanted to, so in this case, let's pick F because it's furthest away. So let's run through that example. Okay, so We will look at F's column, and we will look at that last column, and we can get a couple of pieces of information from there. So first of all, the cost from A to F is 9. Okay, the cost, this table always gives you the cost from A to a vertex. It is not from D to the vertex or from B to that vertex. It's the total cost from A to the vertex. Okay, furthermore, we're told that F came from D. So F's previous is D. That allows us then to use the column D and to chain a path. Okay, so you see we're chaining a path, and we're just going to read this path backward. Now we see that D came from C, and so we're able to look at C, and we see that that came from A. Okay, and the fact that A has a -1 in its previous tells us to stop trying to find any other connections. And so the path then is A to C to D to F at a cost of 9. And that's Dijkstra's algorithm undirected graph example. This is a note I made earlier, which is that this is the single source shortest path. Again, it is from A and from no other vertex. If you feed it D, for instance, as the starting vertex, you would have to run through this whole process, and you would get different numbers for the various vertices. Okay, having walked through an example of an undirected graph, I want to cover a directed graph example. This will go a little bit quicker. And so we'll fill out this table manually. We'll once again use A as our source vertex, and so it's the only thing in the open list. So we basically are processing A, and from A, which has a cost of 0, I can get a cost of 10 to B, which improves B because B is at infinity. So 10 through A. I can get a cost of 3 to C. And I can get a cost of 20 to D. Now you notice that we're having to honor the directed edges here, okay? And so nothing connects A to E at this point, and so this is the totality of it. And so what's in our open list now is B, C, and D, okay? And so this one is still at infinity. And so we must now pick out of these three the one with the lowest cost. Well, that's vertex C, which has a cost of 3. And so we will take C here, which means that B and D are still in here. And okay, and so C has a cost of 3. And if I go to B from C, I can improve that cost from a 10 if I go through A to a 5 if I go C and then B. Okay, so 5 through C. Okay, and let's look at D. C has a cost of 3, but C has no path to D, no direct path, so C can't improve that particular vertex. And then let's look at E now. C has a cost of 3. To get to E from C, it's a cost of 15. That gives us a total of 18, which is better than infinity. And so 18 through C. Okay, and so this remains as is. And now we add, since we just improve this vertex. We add it to the open list. And now we have B, D, and E on the open list. B is the next one to come off because it's got a cost of 5. D has a cost of 20, and E has a cost of 18. So we pull off B, and that leaves D and E on the open list. And B has a cost of 5. And so from B, I can only go to D. Cost of 5 here, additional 5 to get to D makes that total cost 10. Right now, the cost to D is 20. So we will now go through B to get to D. And okay, so there is no direct path to E, and so we just simply bring that value down. And there's nothing else on the open list. Now out of D and E, D is the minimum node, so we pull that off. Okay, and so I still have E on the open list. And from D, at D I have a cost of 10. If I add 11, I can get to E at a cost of 21, but E already has a cost of 18, so that's a better cost, and so there are no changes at this particular instance. And then finally, we pull off E, and the open list is now empty, and E has a cost of 18, but all of the other nodes, A is cost 0, B is cost 5, C is cost 3, and D is cost 10. All of those nodes are less than the cost of even getting there. So at this point, we're done with the algorithm. So let's look let's figure out what our path to E is. So we will look at this particular node, which is the last node that changed for E, and we'll notice that the cost is 18, so we can write that down. And we also notice that E came from C. Okay, and so we will now look at C, and we see that C's previous is A, and that came from A. And we see that A has a -1 in its previous, and that tells us that to terminate. And so the path is A, C, E at a cost of 18. And that's a directed graph example using Dijkstra.